Hello, my name is Colin. Here, I will talk a little bit about Math Physics Academy and what I hope to do with it. With Math Physics Academy, I hope to contribute to the development of a new math and physics undergraduate and graduate curriculum. This will take time, so as a start, I will begin with building a foundation composed of teaching materials, educational resources, and tutoring services. I want to share a personal anecdote. My first exposure to, quote, programming, unquote, happened in my freshman physics course with a popular Python package, VPython. VPython is very user-friendly, and even a silly first year and his lab mates whipped up quick little physics simulations with a breeze. Some years and degrees later, I find myself on the teaching end of the stick as a graduate student in a physics department. I must be honest, I found it incredibly frustrating. Many things had changed, not just the role I played or the university or the department, and I knew my frustration could not be logically directed at struggling students. As a first year student, I wanted to know things that I couldn't even imagine. I thirsted for a university physics and mathematics education, but it felt like the reins had been pulled back terribly far on all fronts. Somehow, I had taken 3 to 4 semesters of analysis and even the second semester linear algebra before encountering groups and rings. Now, I can't necessarily blame anyone besides myself on this one. Now, as in then, from my point of view as a lab instructor, trying to get students working with vectors from day one, in particular, those students who had not seen vectors before, as well as those who had not, quote, programmed, unquote, prior, I struggled communicating how to work with these simple concepts and tools. By this point in my life, I had spent enough time simmering to be thoroughly fed up with the way vector spaces are introduced in linear algebra class. 8 axioms, sometimes split up into 2 sets of 4, one set with addition and a 0, and one set with multiplication and a 1. Just check whether or not a space satisfies these 8 axioms, and there you go, vector space. I despise this approach, even if my own could use some improvement. Enough, I thought. There are some things that are better communicated than not. I want these students to get over any strange hesitation they have with working with vectors, with encountering vague, abstract terminology, and start learning already. My thinking is, if they are in this classroom, they know how to add, subtract, multiply, and divide, or not, with 0 and 1. They have encountered the words associative and commutative before, so they can learn a new word on day 1 in my lab. A group is a set capital G with a binary operation, we'll call it star, satisfying the following properties. The binary operation star is associative. There is a so-called identity element in the group capital G. We'll call it E. And every element, little g and capital G, has an inverse, which is often denoted just g to the negative 1. And that g to the negative 1 is also in the group capital G. Of course, if star is commutative, the group is called abelian. And perhaps maybe we could have chosen the letter A instead of the letter G so as to not trip over our words, but I digress. If I have to teach students about vectors and each and every one of them is in an engineering or scientific discipline, it's not going to hurt them to learn what a group is, especially when they're reassured they've seen all this before under different names and have already used these concepts before, blah blah, etc., etc. It's almost simultaneously new and stimulating, all the while familiar and boring. Could I do better? I imagine so, with some iteration, so it's worth a shot, I figure. Now that I've written down what a group is, illustrating it with straightforward real numbers or integers, noting the cases of addition with the identity element being 0 and multiplication with the identity element being 1, I can hand wave a better definition of a vector space to the students. A vector space is an abelian group, which we will denote with the ordered pair capital V, comma plus, where plus is a binary operation on capital V called vector addition. The elements of the abelian group we call vectors and typically denote them either in boldface or with an arrow. Along with our abelian group is something we call a group action. Now, a quick aside, I don't necessarily go in depth on group actions, nor do I think this is necessary to do with students, but it is part of the definition route that I have chosen. So, anyways, let's get back. What is a group action? Well, it's some kind of external operation by a group on another group, let's say. And in the case of our abelian group of vectors, we have a group action by either the real numbers or the complex numbers. And yes, the fact that the real and the complex numbers are groups themselves is emphasized to the students. We call the elements of this group scalars, and that group action we call scalar multiplication. I think with the right amount of hand waving, this can go over quite smoothly. Well, let's give some examples to try and see what I mean. When we talk about vector spaces, we also might mention things like its dimension, which of course I've not properly explained up to this point, but no matter. So let's start with what might be the simplest example to consider. The real numbers form a one-dimensional vector space under the addition of real numbers with group action given by multiplication of real numbers. Follow up with yet another familiar example. Three-dimensional Euclidean space are three that we're all intuitively used to, whose elements look like V equal to three components in a tuple, where each of these components is itself a real number. And again, the group action here is given by multiplication of vectors by a real number. We can write out what an operation would generally look like. It is pretty familiar. Students don't generally have a hard time taking this in my experience. Now, the last examples, and possibly my favorite, colors form a three-dimensional vector space, one dimension for each primary color. Green is often used over yellow, however, and I think that's worth noting for them. I want to stress I'm leaving out much detail because with just a definition of a vector space and no mention of norms or products, we're punching air. So we should mention the Euclidean norm in R2, R3, and pick out the properties of direction and of magnitude of a Euclidean vector. Perhaps we can mention vector bases. Now, of course, we should point out the elephant in the room. We have a vector addition and scalar multiplication, and no mention of any kind of vector multiplication. Is it obvious how we should multiply two vectors? This could be a rhetorical question, but it could also be a genuinely useful question to pose to students. Multiplying two real numbers like the magnitude of two vectors is one thing, but multiplying these tuple things together, these directions, ought to bring one pause. Why? Because there appear to be multiple ways forward, I would argue, and it is helpful for the unfamiliar student to consider these questions and perspectives. Having reached this point in my experience, students are rather content with this running understanding that they have, and I can illustrate how to represent some of these ideas we just sketched above in a VPython coding environment. Showing them how to check equality with double equals, using double equals to confirm the expected behavior that VPython vectors are indeed associative and commutative and so on. We are just coding what we have written on a section of the board. Ideally, we could do this with the coding and board side by side, and where each student is more or less following along. I genuinely found this way effective to argue to the student that they already have some prior understanding to these things that are apparently new and foreign to them, and on some level, I believed I achieved my goal of getting them past any initial hesitations they had with engaging with the material. And one thing is for sure, none of these students can ever claim to have never learned what a group is. Admittedly, the mathematician in me takes pride in this. Everything I have shared here comes from my own lived experience, both as a teacher and as a student, and I have not conducted any careful experiments to confirm or support any conclusions I may have already made. I acknowledge many others out there also desire to build a new curriculum with their own approaches and opinions. I hope to encounter more perspectives on pedagogy in mathematics and physics, and I welcome feedback and criticism to my proposals and opinions, ideally in constructive form. And last but not least, thank you for checking out Math Physics Academy. I hope you will consider engaging with us on social media with a like or a subscribe, and please stay tuned for more that we have on the way.